Okay, so the attendance is not very good, so let's wait for a while. Okay, maybe 2 minutes.
One thing to note is that the Canvas calendar does not have class listed for today, but it strangely does have class listed for tomorrow.
So sorry, can you repeat again what you said?
At first glance, my Canvas calendar did not have class listed today, but I just joined the call because I knew that the Canvas calendar was weird. It had class listed for tomorrow as well.
I see. So there's a calendar issue on Canvas, right? I think this class is the last class, by the way. Okay, so we will talk about some other related stuff because you already have 2 written assignments and then final project. So we will not test those things, but we will talk about some other interesting stuff related to data science in this course. Okay. Yeah, let's wait for 1 more minute and we will begin. How would you think? Sorry, I was I took my headset. I think my computer has some problem when just to give the computer sound. So I'm using a headset. Can you explain again? You want to let me know what happened?
Sorry, I was talking while muted. Okay. When I first checked my Canvas calendar, I did not see us having class today. I saw class tomorrow, but now that I check it again, it does have class listed today. So
okay.
It's possibly just an error that I saw, not an error that might be leading to attendance.
Sure. I think it's a Canvas issue. I already sent a ticket and they told me they fixed it, but I'm not sure why this is still happening. I will look into it. Okay. Yeah. Anyway, so this is the last class of this semester. I hope. Yeah, so let's begin. Unfortunately, the attendance is not good. I got some email from some students saying that they are big projects and super busy in the final week. So I understand that. Okay. All right, so let's begin. So today we will talk about what I'm thinking is we will have 2 topics we can go, right? So one is a little bit about deep reinforcement learning, which I think we don't have any course covering that, right? So I previously don't teach this, right? So, but I think maybe for this last class we can teach this. Another is what I originally planned, tell you some ways of collecting data from the internet, right? So like crawling, like using the Twitter API to crawling some tweets and the related data, right? So, and also like using some open data repositories, like US Census Bureau's data sets, etc. Okay, we'll see how much time we have, and then we see how it goes. Okay. Before we begin, so one thing I would like to mention is that we have the idea survey, right? So, and I think the last time I checked, the response rate is not good. So I would like to get your help and help me answer the idea survey of this course. Okay, thanks a lot. Another thing I think the second homework will be due, right? So this week, okay, please be on time. We probably will not consider extension because it's the last weekend. We also have the final project tomorrow. Okay. All right, let's begin. So today we are talking about one particular kind of method called policy gradient in deep reinforcement learning. Before I begin, may I ask how many how many of you already took my machine learning course last, I think, yeah, last semester? Can you like raise a hand in Zoom so that I can get an idea? Yeah, I only see one student. Oh, two students, right? So, okay, yeah. Anyway, so we will have this machine learning course next time again, right? In the fall semester. Okay, so if you are interested, feel free to take. Okay, basically it's a basic course, right? Prepare you with the basic concepts of machine learning so that you have a good mindset for doing machine learning. Okay. So there we talked about what is machine learning. Machine learning is basically learning a function called y equal to fx, right? F theta x, okay? This f can be any model, like support vector machine, neural network, etc. Right? So decision tree, okay? And theta is some parameter set. This is the purpose of training, right? When you train the data, like this is supervised learning, so-called, right? So you give, hey, what's the input and what's the output that it should be, right? And this is mapping, okay? Right, and then you give a lot of training samples, right? Hey, this is input, then I want to see this output, okay? And later when you give it the same data, you can predict the output, okay? And the training is training this theta here, okay? And when you predict, you freeze this theta, which you train, and takes the output, okay? I think these days TensorFlow and, you know, this deep learning hype has made the tools super easy to use, right? Like TensorFlow and PyTorch, right? And now machine learning is more accessible to people. Okay. And there we just talk about this kind of simple stuff, right? So, but actually, if you want to do advanced, like a gaming and like a self-driving cars, etc., right? So you do need depend on your environment and the scenario, you need to take different actions, right? So like turn the steering wheel, you know, etc. Okay. And in computer games, you have the artificial intelligence, right? In like strategic war games, etc. Okay, right. So how these like an AI player decide how to play, right? So that's also need something like reinforced learning. Okay. Yeah, we are looking at one particular method called policy gradient. Okay, which is simple to describe. Okay, and so firstly, reinforced learning, we also call RL, right? So it's actually a branch of machine learning, okay? But it's quite unique because in machine learning, we only have X and Y, right? So input is X, output is what we want to learn from the input, right? Y, okay? And here, reinforced learning is actually a sequence of actions, okay? Depending on, you take an action, you will have some result in the environment, right? The environment status will change. And then you will get some reward. So, hey, this is a good move, that is a bad move. After that, based on the current state, and you will take another action. And this is a sequence of actions. It's like an action trajectory, okay? And like navigating through a maze, etc. Right? So, and finally, if you find the outlet, right? If you find the outlet, then you win, right? Otherwise, you have a penalty, you lose. And there's a reward to tell you, okay? And so this is quite unique, right? So reinforced learning has a lot of unique concepts that are not there in the generic machine learning, okay? So basically, if you want to use one sentence to describe what is reinforced learning, it's taking suitable action to maximize the reward, right, in a particular situation, okay? And once you learn this, you just put this model, you can see the policy, right, how to take the action based on the state, and then it can run automatically by itself, okay? Another important thing is that it's like you get delayed rewards usually, right? So you don't know really immediately if you take these passes, right? Move left, right in a maze, whether you will finally find the outlet, right? So what you can do is you have a sequence of actions, and finally you will say, hey, whether I succeed or not, okay? So there's a delayed reward, and you need to learn from experience, right? So you need to play this thing many times, right? Each time you may fail after maybe a certain amount of steps, you still are in the maze, then you fail, right? If you within that amount of budget, right? So you actually get out of the maze, right? You win, okay? Right, so you need to play multiple episodes of navigating the maze, okay? So here's the concept. And here are some important examples, right? So here we have a maze environment, and depending on where you are in the maze, right, you see it, your eye, right? So, and then you want to interpret into a state, okay, right? Computer understandable state, right? And if you are doing deep learning, this can be using convolution now because it's a 2D image, right? And then you get to your agent. The agent is the decision maker, right? So it's the algorithm basically, okay? And in the meanwhile, after a move, you also need to tell, hey, how good the move is, give some reward, right? And then you will take another action. Maybe you move to a new location, and depends on the new state, you move a new action. And sometimes you can get some rewards in the middle, right? So like you get some like some gold or something, right? So in the middle, and like a bonus time, etc. Right? So then you will get some positive reward. Most likely, you will not get any reward after move until you get out of the maze or you fail after 100 steps, etc. Okay, so you get a negative 200 or positive 200, big reward or small reward. Okay, and these rewards are feedback to the agent to let it tune the actions according to the state. Right. So here we have. So in reinforced learning, whenever, let's say, also we have some like faculty candidate, right, or other invited speech, right? I think a lot of them, as far as I remember, they have reinforced learning components there. Right? So I think last time there's a one talking about smart cities, right? So this is like so electric cars, and they simulate that in a simulator, right? So the first thing when people talk about reinforced learning, you need to ask about the environment, right? It can be a physical environment, okay? Right, you have some sensors capture with the environment, and after the action capture another environment tell you. Right? This is a physical world in which the agent operates, okay? But more often we will have OpenAI Jam, which is a simulator, right? So it's the same thing, right? So in computer, you can compute the physical world and tell you, hey, what happens after this movement, okay? Like you want to keep the pole upwards, right? So how you give the force left or right, okay? Something like this. Right? You don't really need to go to a physical world, because in the physical world, you need a sensor, and there's some delay transmission of the signal, right? So in the computer, if you want to train fast, you can just do this, right? In the game, it's even the case, right? Like AlphaGo, you can just look at the chessboard, right? And each location is like, it's like a 2D array, and you immediately know what's happening and whether it wins or lose, and how many rewards you get. Okay, so then most of the time we use like a environment package. Here the OpenAI Gem has it's like a base class. You implement some functions, and you get an environment, and then you can implement some reinforced learning algorithms. Okay, but anyway, the first thing you need is an environment. Okay, that the agent should operate on. Okay, and after an action, it can change the environment. Okay, and then you have the state. The state is the current situation of the agent. Right? You are in the environment, but you may have some situation, right? So you like scenario here, right? So sometimes it cannot be observed by the agent, right? So for example, if you are playing, for example, you are investing in a stock market, right? So maybe one of the state is, for example, how many money you have right now, okay? Right? It cannot be seen from the environment alone, right? So depending on how many money you have, you can take the decision. Environment is more like, hey, now you, the price goes up and down, okay, right? And so this is the situation of the agent itself, okay, according to the environment. And we also have reward, right? So after taking movement, you need to send some reward to the agent. Tell the agent whether it's a good move or a bad move, okay? So this is very important. This is the key why the models knowing whether it's good or not, and train the agent action policies. Okay. So the policy is map agent state to actions, right? In this scenario, like the agent is in this situation, like a lot of money, then you can be more aggressive in math, okay? Right. And you don't have much money, you should be more conservative in math, right? So the different actions, how you, depending on the state, this is called policy, right? And there's also a concept of value. Value is a future reward that agent would receive by taking action in a particular situation. Let's say, hey, right now you are in a particular, let me see. Yeah, in a particular state, right? And if you take this action, move upwards in the maze, what will be the reward? Okay, right? If you move to the right, what will be the reward, right? So this is a, this is a future reward if you take an action. Okay, So this itself can be another function, okay? And yeah, so these are the called values, right? Okay, so what are the common category of methods in reinforced learning? So there are two methods. One is, so both are theoretically driven by so when you see the Markov decision process, right? So it's just this, right? So the environment, those things, and then you take steps and make the next move, okay? So this is all these methods are theoretically driven by the Markov decision process, okay? The first and probably the most, the first algorithm you will hear of is called Q-learning, right? So Q-learning is to learn a single deterministic action from a discrete actions by finding the maximum value, okay? Maximum reward you can take, okay? So let me go to the next slide and let you get an intuition here. But again, we are not talking about Q-learning in this lecture, okay? We have a YouTube video. I think it's awesome, and it not just give you the concepts, but also give you, it's a video series, okay? And how to code in TensorFlow, right? TensorFlow 2.0. And I strongly encourage you to look into that if you're really interested in reinforcement learning, okay? So basically, there's a so-called Q table, right? So in Q learning, you will have a table, okay? And the table is something like this, right? So here, this is the coordinates, right? So your coordinate in the maze, right? Which location X, Y, okay? And this is then what actions you can take. Move to the right, this kind of actions, okay? And after taking that action, what's the value, right? This is Q values in the Q table, okay? This is Q table, this is Q value, right? After taking that, how much value, how much new rewards you will gain, okay? So these are the, right? So these are actually the probability to take the action. So depending on what its values and its rewards, okay, right? But otherwise, this is the probability that in this situation you would take. Okay, so here you will have a table that you iteratively update, right? So how likely will go here or go here, okay, right? And then this table will be iteratively updated by learning a function, right? In this state, what should be the action, okay, right? So, and it's kind of like a table lookup, right? So when you're in a particular location in the maze, then you see, hey, these action will give you different values. You want to find the one that maximizes this value, right? This is like the reward value, right? Hey, maybe here, if I'm in S1, I will likely go to this direction. But then finally, I find, hey, this actually has some negative reward, right? And I will adjust the value down and adjust the value up in the algorithm, okay? So, and then finally, I will take the right move, essentially. So this is basic Q-learning. So what's the weakness of Q-learning, right? Q-learning can only support discrete actions, right? It's a table lookup, okay, right? And there's a concept called deep reinforced learning, right? So it's replacing some, like this table module with a deep learning module, right? Basically, a deep learning module has a states as a neural network input, okay? And the output is a softmax probability vector of whether it takes this or takes this or takes this or takes this, right? So you can replace some of the traditional stuff with some new stuff, okay? But anyway, so Q-learning is only able to handle discrete actions. So what's the problem here? The problem is that a lot of the cases you need a continuous action, right? How much force you push to the left and right to keep it upright, okay? So, and you think about self-driving cars, you have a steering wheel, right? How much you turn, okay? Right, so this is continuous. You cannot say, hey, I go 90 degree, 180 degree, right? But in a lot of simple games, it's good enough, right? Going down, moving up, going left, going right. Okay, so this is okay actually. So Q-learning, again, so this video I strongly recommend you to watch if you have interest. Okay, so Q-learning is learn a single deterministic action from discrete set of actions. Okay, right. So firstly, there's a discrete set of actions. It cannot be continuous, right? Like an angle where you turn the steering wheel, okay? And it has to be discrete because you have a finite number of table entries in columns, okay? Secondly, each is, at this state, after taking this action, how much reward you get, right? So then you will take this is actually a Q value reward. It's a smooth average of the history, okay? Right? So if you get some reward earlier, you will play a part here with some, gamma, with some discount, but you will see that reward here, okay? And then based on this, you will pick the next action with a maximum value. Okay, so that's why it's deterministic. You will not explore other directions until, let's say, the Q value is adjusted down. Originally, if it's 0.9 in S1, this position, you will always go east. Okay, always take this action until maybe this value gets some very negative reward and the model tune it down. Okay, this is the parameter you tune basically. Okay, so here, this lecture we look at the policy gradient, right? So policy gradient, the difference is that it's a direct policy search. Okay, right? So it's not just through the Q table. Okay, what we do is we learn a map function from state to action directly. Right? So and it can be stochastic, which means, you know, in a particular states, right? So you can take this action with 30% probability. You can take this with 70% probability, right? So it's a it's a distribution of the actions. Okay, right? For example, if you look at you know, this you can take a discrete actions like a run or jump in Super Mario, right? So when you take the image, but you can also say, hey, how much force I want to exert on this stick, right? So you can say, hey, on the left, on the right, right? If you do this, it's a magnitude, okay? And you can say, hey, this is a Gaussian distribution or some distribution here, right? Each can take some probability, okay? This is policy gradient, which means you can have different force values. It's a continuous space, right? You can learn it as a regression model, right? So from the input the status, whether you should move to force to the left, maybe positive 10 force or negative 5.5 force, etc. Okay, so this can be continuous. Another thing is because it's a probability distribution, right? So you basically, you will sample from that distribution. So the process is stochastic. Okay, it's stochastic and not deterministic like Q-learning, and it works in continuous action space. Okay? But these are the category of the method. Okay, there are like tens of methods in each category. Okay, concrete implementation, right? Have pros and cons that you can look into. Right. So these so far we are talking about RL or reinforced learning. Right. So due to the success of deep learning in computer vision and NLP, right? So people naturally think, hey, now these neural networks are so powerful, and you can play the episode again, right? So because this is you can, maybe human play is slow, but you can let computer stimulate, right? Your jump, you need to push a button, but in the computer, you can play really fast, like 1 millisecond. You go multiple chess steps, okay? Right, and you can jump all the way, finish one episode maybe in just 1 millisecond, right? Like computer play the game repeatedly, okay? Right, this is what we call learning from experience, okay? Maybe initially you will fail and get a negative reward and adjust the table, and finally you will find a good path, right? So now that we have so many training samples that we can get by letting the computer play with itself, for example, etc. Okay, right? And then what we can do is, this is big data, right? So we know that for deep learning, you need a big data to train well. Because in deep learning, initially people are using statistics methods like graphic models, encoding some prior knowledge there, right? Not using these generic models with every factor collected. You just tune the weights on the edge, right? There are too many parameters, okay? But when you have big data, actually this can surpass the traditional models of machine learning, okay? And then these days, you know, these neural network models are super popular, right? We call it deep learning, not because it's always deep. In some cases, it's not deep. Now deep learning becomes a term not saying the model is deep, it's just saying you are using neural network. Okay, that's a pretty funny situation, but really it's what's happening, right? So you could also call it neural, right? Neural learning, right? Like it's applied anywhere, right? So for example, for recommendation system, you can still call it a neural recommender system, right? If you replace traditional machine learning module with deep learning model. There's no difference in, you know, in here, right? In reinforced learning, we can replace a module, right? Original module in reinforced learning with deep learning neural network modules, right? Then it becomes deep learning. Okay, for example, after, you know, you are in this state, how you take the next action, right? You can use a fully connected layer, right? So multi-level perception, right? You have multiple layers, and use a neural network to do that, right? Previously, we may use some traditional method to do that, right? So for example, for this this Q-learning table, right? Now we can learn this table itself as a neural network, right? This is a stated input, actions, output, right? Machine learning model, as I said, it's a y equal to fx. This is y, this is x, right? You learn the theta here. These are the parameters, right? Okay. So then this becomes a deep reinforced learning, right? And it has a significant, advantage, right? So you know the AlphaGo, right? So all these things like, and there's a deep mind, right? Google DeepMind, and I think a lot of hypes in the area, right? A lot of people are moving in this direction, okay? And I think the self-driving car itself and the drones, right? So drone navigation, like if you know, how to keep balance of the drone, right? And it's probably quite similar to this, right? So how do you adjust the different, in a drone, you probably will have 4 propellers, right? So how to adjust them, right? So keep your balance, right? And you can even, there's functionality you can, the drone can automatically follow you without controlling it, right? So then you can shoot a video that you are walking in the environment and it's very stable, etc. Okay, so all of these are using deep reinforced learning, often deep reinforced learning. Okay. And so usually, like if you want to just do replace a policy, the Q table, and you don't know the stated vector, then you use deep, dense layers, fully connected layers, right? If other times the input could be a game image, right? So in this case, you take a camera somewhere, right, to the screen, or you have some way to pass a screen signal to your model, okay? And then this becomes an image, a frame, right? Then you use convolution net to extract the information, right? This thing becomes your state, okay? The state is these pixels, basically, right? Convolution net will figure out what's the semantic meaning of this, right? By stacking multiple layers. Each layer, the neural units, maybe higher level stuff, right? So maybe, hey, the cloud and some like other, like a flag, etc. Okay. And finally, you will have maybe the dense layer by binary classification, right? Translate the higher level features into the action, right? Doing a softmax, etc. Right? Whether you should continue run or you should just jump. Right? Okay. All right. So here are some reinforcement applications, right? So the most popular 2 applications you heard of is one is robotics, right? And often with hardware, okay. And then it's purely software, then often it's games, okay? Right, so robotics, for example, the drone itself is a robotics, right? And the self-driving car, you can say it's a robotics, right? And I think this is by Google DeepMind, or these days, either Google DeepMind or OpenAI. Maybe this is by OpenAI, by the way, okay? So OpenAI and Google DeepMind are two AI startups that are companies, right? Because DeepMind is purchased by Google now, right? So they have tons of money. So maybe it's not a startup anymore, right? So anyway, so you can see that these 2 are the leaders in the reinforced learning field, right? So they deep reinforcement structure. They have device in the arm that can play. How do we call this, right? So anyway, so they can play different games using robotics, right? Or just simulate the game inside the inside the computer, right? So like a Go, it's a Go game, okay? And like other simpler games, okay? So the fastest way of getting you started on like programming reinforcement learning stuff is really if you start with some environment, right, which is OpenAI gem. Okay, it's by OpenAI. Okay, right, so they have a gem, which means it's an environment where you can play and take actions, etc. Okay, and the environment object in Python, right, has some functions that you can implement your own environment, and they also provide these like a predetermined environment. Then you can learn, and then like this car, how to turn the steering wheel not to hit something. Okay, it's pretty interesting stuff. Right. Any questions so far before we move to policy gradient? Yeah, so if these slides are just to try to build a reinforced learning mindset for you, right? So you need to be aware, hey, these are the concepts you need to know. If you don't even know this, maybe you are wasting time when go to a talks or like a tutorial on reinforced learning. Okay. And this is the environment that can quickly help you start with reinforced learning. Okay. All right, so next let's move on to policy gradient, right? So yeah, again, this is a recap of some basic concepts, right? So you will have an actor that knows what action should take, you know, when you are in a particular state, right? And after taking the action, the state will change, by the way, right? So you can have a video game where you manipulate this wheel, right? So this stick, right? And you can like an AlphaGo is an agent, right? You play with the human agent, right? So and beat the human, right? So okay, so that's an agent here, right? Essentially, it's a machine learning model there, right? So and there's also the environment. Okay, the environment is where after taking action, how you change the state, right? So this is the environment. Right? Okay, if the simulator, then immediately it computes the next environment for you, right? If the human, then you need a video or some other sensors to collect the information and put into the computer, okay? And there's also a reward function, right? So reward function is something like, hey, after each move, right, what's the value you get, right? Okay, so this is like a get 20 scores when killing a monster, right? So then you will, the game will try to kill more monsters, right? So, and, you know, and here there's like a rule of go, right? So it's a little more complicated. Like if you are surrounding like you are surrounding other people in then you can win. Okay, so anyway, if you know go, then you know there's some rules that can decide your reward. Okay, and let me see. Okay, so we are learning this actor, or we call it the agent, right? We are learning this actor's policy, right? Okay, so here what's the machine learning module here, right? So the machine learning module is really something that is called a policy. Okay, what is the concept of policy? Policy is once you see a state S, right? How to determine which movement you should take, right? So this is the output Y. Okay, so reinforced learning is more like a whole set of concepts. Okay, a whole concepts like here, right? But within there, you cannot control the reward, right? So because after move, how much you win, it's decided by the environment, right? So it's actually by the rule of the game, for example, okay? And the environment is also not you can control. All you can control the actor. So apparently, you know, the machine learning module is actually in the actor side, right? So what the actor can do is depend on the state of what action I take, okay? So state is input, action is output, okay? So in this example, for example, when you see a game where you want to kill some monsters on top, right? So you are maybe some flight here, okay? Then you can also have multi-agent, right? One is you, one is another friend, right? Okay, and then you want to decide, hey, for the next frame, right? Or next time step, where should I move? Okay, left or right? Okay, or forward, etc. Okay. Oh, here we can only go left and right and fire. Fire means kill the monster. Right? If you are not aligned with the monster, you basically waste the fire. Okay, and it takes time to move. Maybe the monster will come and catch you. Right? So okay, and so here's the example, right? So you can have a image. If it's an image, of course, we need to use a convolution operation, right? Take image, right? Instead of using the dense layer. Okay. After that, it will translate by the final dense layer into, you know, the action, right? You can take each with if you know the logits and softmax, right? So it's a probability that you can take. Right? So this is like the score of the action, this probability you can take, and then you will flip coin, and if it's 70%, then you go left. 20% you go right. Remember, this can be a stochastic process, which is by itself good, right? Because you will get out of the local optima, right? So maybe there's some gift on one side, but after that, taking that gift, you will find a monster killing you, right? So then you initially you will move there, but getting the negative reward, you will go right, for example. Okay. Right. So any questions? So the machine learning component is really here. Okay. The model is here. Okay. State, how to translate state to the next move. Okay. So that's the machine learning model here. So naturally, if you want to, maybe previously we have a Q table, right? Now we want to replace it with some neural network stuff, right? So deep reinforcement. Then we can replace with a neural network. Okay. So here's an example of taking move. I start with this image, okay? And then you have a green dot here, okay? Then what you can do is actually, the action say, hey, now in this image, you should go right, okay? With high probability, then you sample and you should go right. Then you will move to the right, right? Originally here, now you move a little bit to the right, okay? And then you don't get any reward. You don't kill monster. Remember, we say kill a monster, you get 20, okay? And then after here, you say from prior experience, it says, hey, you should fire, right? Hey, oh, these are aliens, by the way, okay? So you can fire, and then you will hit maybe this alien, okay? And then you will get some reward 5, okay? This alien is gone, right? So some process like this, right? And you repeat this after many turns, you can obtain a final reward, okay? The game over can be the 2 cases, right? So one case is your aircraft is destroyed by the alien, right? Maybe they can fire or they can catch you moving towards you, okay? I don't know what the game is functioning. So yeah, anyway, so another possibility, you actually are surviving, then you have to kill all the aliens, right? And then the environment will tell you, hey, now it's the end, okay? You win, right? And maybe you win, you will get a big reward, and combined with a prior reward, etc. Okay, or you just get the final reward. But when you lose, you should penalize yourself, right? And if it's 5 per monster, then your use you should give a -500 or -300, right? It's even worse than killing all the aliens to reward, because if you lose, then you don't get a chance, right? If you move, maybe you didn't get any reward, but you're still surviving. Okay, so you need to have some way to decide the reward function. Okay, in the machine learning literature, a lot of people are just using the reinforcement learning application, not actually designing new algorithms. In those cases, what you are doing is you design the reward, right? And you design this neural network, okay? This neural network. And you run the library and see whether you can learn a good policy, okay? And here each step you will have a reward, right? Sometimes you kill the monster 20, sometimes you don't. And sometimes you are killed by the monster, you take a -500, okay? Then this reward will be feedback, and then you can adjust the model, okay? You can adjust the back propagate, right? You get the reward, which is not good, right? So because you want to improve the reward, but it's negative, okay? Any questions so far about these basic concepts? Okay, so then let's continue. Yeah, so again, so these concepts should be clear, okay? So you can call it actor. Sometimes you see agent, sometimes you see actor, okay? It's the same thing, basically. And you have the environment, you have the reward, right? So in the policy gradient formulation, we are thinking about something like this, right? So here you have an environment. Right now, initial environment is S1 state. Okay? Environment tell you, hey, now this state is S1, okay? And then you will fill this S1 from the environment to the actor. And the actor will see, hey, now you are in state one. According to the neural network, it tells you, hey, you should take action A1, okay? This A1 will be fed back to the environment. And after this movement, right, so you should change your state, S2, okay? And this S2 will be fed to the actor again. I can say, hey, now after this movement, it's like this situation, then I should take this action. And this can go on, okay? So you can regard this as a state action trajectory, right? So this is the first state, you take this action, and this changes to the second state, then you change to another action, etc. So you can regard this as a trajectory. And we use Tor to denote this trajectory. This is like one episode how you play, okay? Right. And for in here, right now we assume that the game is like this, right? So after playing the whole trajectory, you will get some reward. Like if you win or you fail, right? So for example, whether yourself is destroyed or you kill all the monsters, right? And the reward is associated with the trajectory at the very end, okay? And here we can use conditional probability to respond it, right? So basically, this is the joint probability that we see S1, A1, S2, A2, ST, AT, right? We can decompose it, right? So because of this reason, right? So if you look at here, A1 is so this is using the graphic model, right? So dependency. Okay, so how to say this? So A1 is depending only on your first environment, right? So if you take these two steps, it will become P A1 S1 joint probability. Okay, I think you should know this, right? So in probability theory, continual probability times this S1 is your joint probability. Okay, now you come to here. Okay, and now these two terms go into condition, right? And then you have the state S2, right? And then it will be a joint probability of S2 here, okay? S2. And then you have this, right? So here we actually do some simplification, right? So the action 2 is decided only by the state 2. It doesn't depend on the historical, how you move to state 2. It's right now at the state 2, right? This is called the Markov decision process. We just look at one hop, okay? Now that I'm at state 2, how we decided A2. Basically, we are saying, hey, now P A2 S2 is equal to P2 S2 and all the previous ones, right? S1, A1, S2, okay? But these have no impact, only S2 have impact. But if you expand the other two terms also here, then you can see this is joint probability, right? If you take time this thing with this thing, these are all in conditions, okay? Then you will have A2 S2, okay? And this process can go on, then you will get the joint probability of this trajectory, right? So this is basically the concept. But we have the Markov assumption that your action, right, only depends on this S2 is only input. It encodes all the information. You just need to S2 to decide it, right? Okay. This is our assumption here. Any question about this? Oh, okay. If not, then let's continue. All right. So let's assume we have T moves. Okay. Right. T actions in the trajectory. And now, so how can we consider this? Like, so you can see this is one component, right? We can write it like this. Right? So how when you add a state T, how you go to take which action? Remember, this is our machine learning module. So it's F theta. We have theta that we are tuning. Okay. Maybe a neural network, etc. Okay. The second one is after you take this action, right? Then you throw back to this environment, and the environment change to another state. Okay. Right. And of course, the environment actually also need to know the previous state and then the action. Then you know the next state. Okay. Right. And for this thing, it's out of your control. It's the environment. Okay. Right. Of course, you can code like your environment, like OpenAI gem to react. But the environment in general, in physical world, is out of your control. What you can control is this thing. That's why you have theta. Okay. Where the training is really to find a good theta so that you can maximize the reward. Any questions? Okay, I hope this is fine. So the special case is this one, right? So this S1 is the initial state, right? You don't depending on, like S3 depends on these two, S2 and A2, right? But the initial state, you just put it outside the big product, okay? All right, so any questions? If not, I assume this is okay, right? So this action probability can be represented like this. And now, so this is just how to map, right? So how to map the input to output and how to compute how good, like the trajectory's probability, okay? Then if you take this movement of probability, what do you want, right? So you want the reward to be maximized, okay? Right. So then we need to give some feedback for the model, right? If it's deep reinforcement, we need to have the loss function so that it can back propagate, okay? So we are doing so-called expected reward because this is a stochastic process, right? If you remember, we can go to the left with 30% probability and go to the right with 70% probability, okay? So this is really a stochastic process and we can only compute the expectation, right? Right now, if you are here, it's not deterministic, right? In Q-learning, maybe the episode will be dismissed in some way, but here, no. It's next move, you are most likely go to right, but you can go left, okay? Then we need to take expectation, right? We know that expectation is something like this, right? So you have different ways of play this game, right? So have a different kind of trajectories we talked about, okay? But each trajectory has a certain probability. That's what we mentioned in the previous slide, right? So this is how you compute the probability, but depending on how your actor, the parameter is looking, okay? Now, expectation is, hey, for this trajectory, you have this reward, right? For that trajectory, you have that reward. You will sum all them up with times their probability, okay? Right. Then you will get the expected reward. Any questions? So we can say that this is, you know, your expectation of your reward, depending if you sample your trajectory according to the probability model, okay, the probability distribution, which is actually propelled by the theta that you try to learn. Okay, so now let's look at what the individual reward, right? Individual reward, we know we take T steps, right? This is the first step, this is the second step. We just sum them up, okay? Later we will see that actually summing them up is not good enough. We will have some discount, okay, right? Like, but we'll go to that detail later. Okay, right now we assume the whole trajectory is associated with one unique reward, okay? Right. At the end, you will get some reward, okay? If that's the assumption, then we can simplify things. And we are just saying, hey, if you take some gold, then it's fine, right? So, but finally you fail, right? So maybe take a negative 1,000. The gold is just 20, in Super Mario, for example, it doesn't help, okay? And then the whole trajectory has a unique reward here. Right? This is what we are looking at. All right, so the key idea of policy gradient is as follows, right? So remember, we need a gradient, right? So taking gradient to adjust the policy, right? This is back propagation. Now, based on this loss function, right? So we want to, so this is not loss function, okay? This is called a reward function, right? So the reward, right? So because in loss function, we want to minimize loss, right? In reward, expected reward, we want to maximize, okay? So that's why in reinforcement learning, we are doing gradient ascent, right? You move towards a direction that increases your reward most, okay? Right? So you are not doing gradient ascent, okay? So here, what we are doing here is this, right? So now, after playing these games, right, a bunch of games, finally you say, hey, again, this is an approximation. You cannot play all possible actions, right? If you can move along 4 directions, each step you have t, so you know, 4 to the power of t, right? It's crazy. So usually we will sample a batch of trajectory actions, okay? Play some episode. We cannot enumerate this, but here our derivation assumes that you can really enumerate all the possibilities, right? Sometimes it's not even possible because, you know, what if the action can be continuous and this is integral, right? You can never exhaust it, okay? We can only sample in some sense, but we'll see those details later, okay? Assume then this contains all the possible actions and take complete expectation, right? And then now that you have this expectation, right? What you can do, but again, this is crazy, right? You just take all possible trajectories, okay? And what you can do, you can see, hey, how good overall the expected reward is, right? And then you can adjust your action, okay? Adjust action parameters. So then it will say, hey, in this scenario, you go left with lower probability to avoid being killed, for example, right? And then after taking gradient towards theta, right? Then you know the gradient of theta, and then you can do gradient ascent to sum them. I think there's a, let me see. Right, you can do gradient ascent, right? You have a theta, you have the gradient of the reward function to theta, right? And you go a small step towards the direction that improves your gradient, okay? So this is how you update the model. Okay, so now let's take a look at how to calculate this, right? So this concept is clear, right? But this calculation is a little bit complicated, okay? So how can we do this, right? So here we need a trick, actually. Okay, so let's take a look. So here, this is our definition, okay, right, of the policy gradient, because this is the reward is this times this, right? And we take a derivative, and the theta is only associated with this thing, right? So then we take it only to the p theta, okay? And now that we do this, we do a simple trick here, right? So we divide by a value and multiply it back, okay? So that doesn't change the quality, right? But this actually can give you some nice property, because who can tell me, let's say if you have log x, right? Log x. If you take a derivative over log x, what's the result? Who can tell me?
1 over x.
Yeah, it's 1 over x, okay? 1 over x dx, okay? Dx. We can write something like this, okay? So we are using this trick, right? So, you see this is dx, this is x, right? So if we consider this component like this is really the gradient of, the log of this x, the p theta, okay? So we're using this, right? So this is I think I forgot the name, it may be the log trick or something, okay? So that's why we construct this, okay? And in general, we can just memorize this, right? So, the function x, and you have, so here we are putting this x in a function x. It's the same, basically, okay, because of the chain rule, right? So gradient of this function, you can directly memorize this, and it's equal to the function itself times the gradient of log that function, right? You can also get something like this, directly go from here to here, right? Any questions? If this is okay, let's consider this term, right? So what's interesting about this term is this is a summation, this is the probability of this trajectory, and then some value when you have that trajectory, right? So this is expectation, okay? This is again the expectation. Then these two go to here, right? So now we get this this very nice form, okay? This very nice form that we just want to take expectation of your each trajectory's reward times, because we can compute this log PCSA, right? It's from your neural network, if you remember. These properties from your neural network, okay? So let me see. So you can take a log of that probability and then take gradient over theta, right? So it's basically you can code your neural network to take a log of that probability, right? Okay. Right. So the only trickiest thing here is that you cannot exhaust all possible trajectories following that your actor's theta, okay? Right. This is a large sample. So what you can do is you can play the game multiple episodes, okay? Right. You play for a long time, and then you have n episodes, n samples, okay? And you take the average, right? This is like a estimation, the sample mean, okay? This is not a true expectation, but it's very close to the expectation, right? And now we can go from here to here, right? So what we are talking about is this, right? So if you remember, what is log p, okay, right? So the log p is actually, if we go to the previous slide, yeah. So we have p equal to this, right? If you take log over both sides, okay, you take log, and the log of AB equal to log A plus log B, right? So this becomes log of this, some log of this, some log of this, and some of theta, okay? So this will become something like this. And what will happen is, so take gradient over the log P theta will become the summation of the gradient of those individual terms here, okay? And you can see we only have this term, right? So this is your agent relevant theta term, okay? The reason is because the other constants are not changing with the theta, right? So this term is the environment term. No matter how your theta is, this is not relevant. After taking gradient, this is like the term that is relevant to your gradient, okay? After you can add another term like, let me see. You can add the other term, which is a log theta, no theta, okay, this is why it's gone, okay? Log the other p state, right? If your previous state and the action, okay? But this term has nothing to relate to c after you're taking gradient to theta, because this thing has no theta, this term is 0, okay? So we can just ignore it. Any questions so far? Okay, if not, then here is how, if you are writing your code, right? This is what you will be doing. Okay, a lot of the time you can just using other people's algorithm, but you encode the model according to your need, right? So the state of the reward function. Okay, if you want to implement the gradient itself, positive gradient itself, then you know the function, right? This is where you get the model output, right? The last dense layer, the softmax output, and then take a gradient, take log, right? And then this thing. You need to take a log, and then you backpropagate, okay, with the reward function you get, right? So this is where you can see we need a reward, okay? So we do need the reward to compute the gradient of theta, okay? So this reward will come in, okay? All right, any questions so far? If not, let's look at an example, right? So here we are, remember, so this gradient is actually equal to, this is called policy gradient, right? Actually equal to your reward of each trajectory times, the gradient of the log is the probability that you have the joint probability of the trajectory, okay? And which you, as I explained, you can all compute it, okay? Then let's say this is the first episode, you do this, the second episode, you do this. And we assume all of them are using the final reward you get, okay? The weight is the same. We will relax this restriction later, okay? Right, so then you will compute this. Right? So because, when they are the same, then you can take into the summation, right? So any questions so far? So this is basically you compute this gradient and then you put into here, then you can do gradient ascent, okay? Because we want to maximize R, not to minimize R. Okay. All right, I hope this is fine. So there are some, when you actually implement stuff, right? So you can actually, this logger function is usually neural network. You have the state, you have the input, you extract features using all kinds of like convolutions, etc. Right? Finally, if it's a classification problem of a discrete set of actions, what you do is you add a dense layer, final dense layer with 3 output neurons, each represent a action. Okay, and then you do a softmax to get the probability of them, right? And then you can use PyTorch to add a log function, and then the loss function there, and they will take the gradient for you. Okay, you can call the, I think it's a gradient tape or something. Okay, and then you can get the gradient, and then in those libraries, again, so it's good to learn some of those libraries. There are tutorials online. Okay, on my website, I actually shared a very good video series on this tutorial. I mean the personal website. You can look at the. Yeah. Any questions?
Charlie.
Hello? Sravan, you have any questions? Hello? Yeah, if not, I will mute just to be. Okay. Yeah, so let's. Right. Okay, so the reward is actually the reward function that you get, right? So this is coming from the environment, okay? The environment determines if you are killed, then you get a very negative reward, right? If you get the monster killed, each is 20, okay? All right, so yeah, so there are some tips in the implementation, right? Naively implement these two things. Actually, can have some problem because if you remember, this is sampling process. Okay, this is sample. We only try to play n episodes, but the reality is that in our derivation, assume we try all the possible trajectories, right? But this is only a very small fraction of that trajectory. So what will be the problem here? Okay, so it's possible that in the ideal case we have 3 actions we are taking, right? So and they are like this, and after taking this adjustment, the probability looking like this, okay? But because of the issue of sampling, maybe in some cases, right, so we happen not to sample A, okay, this possibility, okay? And after softmax, what will happen is, I think this blocked it, okay? So what will happen is that A, originally you see actually the gradient of A is big, it should increase, okay? But because it's not sampled, right, so these two will increase, but this guy will decrease a little bit, right? So actually this is not because because of the gradient not there. It's because you are simply not sampled that trajectory that will take this action, okay? Right, then this action, let's say you try the 3 trajectories, none of them go left, right? And then you will penalize it reasonably because actually if you try another trajectory that go left, you will find a large reward, okay? Right. So in order to adjust, combat this sampling issue, we will adjust this reward function by minus b. Okay, b is what we call the expected reward, right? So you can track the expected reward. Let's say this is also particularly important if you have like a reward that's never negative, right? You never die, but you just see within maybe 2 minutes how many monsters you can kill, right? It's always a positive number. Okay, in that case, you always get positive rewarding. It's okay, but you increase and you will do softmax to adjust. Right? So, the problem is that some of them are not really good compared with the average case, right? So for example, even though this action is sampled a lot, but it's not good, the gradient is small, okay? Then after you take minus the running average of the historical rewards, you will find, hey, this is not really good, right? And this will become a negative. Okay, it will try to adjust it downwards instead of upwards, right? So it will not penalize this, because when you adjust this upwards after taking softmax, this will downplay this. Now this thing will not downplay. Okay, so this is the trick that you need to actually adjust this function, right? So because this is a constant in some sense, right? It can change as you have more episodes, right? Let's assume this is a constant, then the reward is still the same. Okay, this is minus a constant, right? If you minus this by a constant, if your theta originally maximized without B, now with B, you still maximize the reward. Okay. Any questions? Right. So again, deep learning is full of tricks, right? Because if you directly implement without B, then things will not train. Okay. And I mean, machine learning. Okay, there's a lot of tricks there to make things work. Another is that you can assign suitable credits, right? Previously, we talked about, hey, you finished all the episode, right? And then you see, hey, here I get some gold. Here I get some like I was detect some blood by the monster, right? So in that case, you will have this episode of final reward is 3. Okay, and here you get killed by a big monster, or damaged by a big monster and a small monster. It's -7, right? And in that case, then we will do what? We will get the entire. Let me see. We will give if you are computing this, right? So all these trajectories, okay, all this episode, you are using the same reward, right? So always 333 and the -7, -7. Okay, so for all 3 of them in this cumulative sum. But this is not good actually, right? So because you think about it, now if this is your SA, right? So you take action A1, you go to SB, right? But no matter how historical looking like, right? In SB, you take A2, the same action, you reach the same S3 and A3, right? Then this thing should be, should be kind of like the reward is, because this is regarded negative, right? But if you think about this, because the historical ones is positive, it actually makes the reward here positive, okay? Then it will boost the chance that you take A3, okay? But actually it should penalize it, because no matter how the historically you're +5 or -5, when you're here, right, take this action, actually you're negative. You should avoid taking this A2, okay, at SB, right? So the previous scheme is not good. So, okay. So what we can do is, let me see, what do we have? So one way we can do is this, right? So we just forget about whatever is before me, okay? When I compute the reward for AT-ST, I consider TET plus 1 T plus 2, but not a 1 to T minus 1, okay? This will adjust this relay becomes -2, and this is also -2, right? It doesn't have the impact of prior actions. As long as I'm at this state, okay? This reward should be adjusted to this value. So in this case, for these 2 terms, when it's here, it will always be -2, okay? So this will also improve the performance of it. Right, so here's, so this is basically what you do. Now, starting from right now, right, and all the way to the very end of the game, right? I don't consider the historical one, which will mistakenly affect the gradient, okay? And yeah, and finally, so this thing itself can be a function, right? So you can even learn it with a theta, right? So when you, right now we only talk about the actor, the action theta, right? So the reward, right? So the advantage function itself can also be dependent on theta, right? So, and so this is can be estimated by a critique, right? So we don't have time to cover that, okay? But so there's an actor and there's a critique, right? So this actor, this critique model, okay? Right. So then you can also consider the critique part and adjust the theta, right? Another thing is that, we will have a penalty, so-called discount factor, gamma, like 0.9. And it's like a, right now you are T, right? If you consider the reward from future, right? The further you are, like the future T2 prime from the current snapshot, right? then the less it will play a part in your impact. Let's say here, right now you're here, right? You get -2, it's fine, right? But maybe you play somewhere you get a positive 100, okay? But this will be discounted by maybe 0.9 to a large factor, okay? This is gamma. And because there are 100 steps after time 100, this is a really small impact, even though it's a 100, but it's gonna be low impact on this step right now, okay? So the gradient on this term in the summation, okay? Right, this is reasonable, right? This actually in Q-learning, we also have something discount there, okay? If you have interest, you can take a look. So basically, if you are many steps away, you need to discount the reward to you, okay? But you do need to count some of them there back, okay? Because that's a lot of cases you don't get reward in the middle, you get the reward at the end if you win or you fail, right? Like the Go game, okay? Right. Go game, you will also get like the you can take out some other people, you can get some reward in the middle, but some of the games, like in maze, right, whether you get out of the maze or not, right, you really get it at the very end. Each move, you don't get any reward. It could be 0, okay? Right, so this is this concept. And again, so here's a link. I will upload this slide to Canvas. You can take a look. Okay, so these are the algorithm categories. Okay, like a policy gradient. They have been tens of algorithms proposed. Right? Each may be more than 10 for sure. Okay, for Q-learning, they also have tens of algorithms. Especially now that they have deep learning. Right? How to combine deep learning into this framework and adjust different kind of models. Right? So there are many ways, right, that people can play with it. That's why you see DeepMind and OpenAI that have huge amounts of papers. Right? Okay, so that's the end of this slide. Any question? Again, this is just a kicking you start on this stuff, right? So then if you are interested, you can look into here. There's a bunch of algorithms. Let me see. I know that just to make sure, how many students here are PhD students? I think 1, right? As far as I know. Because of the pandemic?
Yes, sir. One student.
Oh, 1, yeah. So
one.
Yeah, so if you are doing PhD and you are interested in this topic, for example, talking to your advisor, or you are doing master, you want to find an advisor and learn these things, right? So you can do a polygradient, or you can do a Q-learning algorithm, right? So there's a I think deep Q-learning or something, right? So there are a bunch of algorithms, okay? And then you can also just use the algorithm to address the real-world problems, right? So DQN, and there's a DDQN, a lot of algorithms there in the Q-learning, okay? So something like deeper with double DQN, right? And there's also DRQN, etc., right? In the Q-learning, deeper recurrent Q-learning, okay? And because these days deep learning people are like publishing paper like crazy, right? There's so many modules you can combine and try, okay? And yeah, here the policy gradient, you also have like actor critique, right? And you can also have, the basic one, we talked about the vanilla policy gradient, right? So you can improve it, right? And there's so many, like PPO is one used by OpenAI by default, I think, okay? Right, so if you have interest, right, so you can do a survey of this for master thesis or PhD thesis, etc. Right? Okay, a PhD level 1, etc. Okay, that could be interesting. Just some suggestions. Right. Okay, any questions regarding this slide? Okay, so basically this page is by this link. Okay. All right, so that's the end of the first part of the course, the class. Okay, so the lecture. We will then look at the data, how to access different kinds of data. Okay, originally we have some mini project for you to practice how to collect the data, but I think we don't have that time this semester. So we will just tell you how you can collect, and in case you are interested, you can go there and look into it. Okay. And yeah, so I will also upload those slides on Canvas. Then you can, after the course, if you are interested, you can take a look at it. Okay. All right, so it's 6:10. Let's take a 15-minute break. We'll come back in 6:25. Right. Thank you. Again, so if you have any question, feel free to ask now, okay? Because I will be leaving maybe after 2 minutes.
Yeah, Professor, are you going to take attendance this lecture?
Yes, I will take attendance in the second half of the lecture.
Okay.
Any other questions? Okay, so then I will see you in 15 minutes. Okay. Okay, so let's begin. So one important thing about the data science is you should know where to get data, right? So a lot of open data sets like Kaggle, but these are historical data people prepared for you, okay? You might want to collect your own data, right? So a lot of cases, for example, Twitter has an NLP data and some meta data like a graph of who is following who, right? And Twitter is a very interesting place where people collecting data for analytics, okay? And you can give your keyword and search for whatever you are interested in, right? So again, so we don't have this program project this semester, okay? So basically what you need to do if you want to cross things is you need to have a developer account from Twitter, okay? And then they have the Twitter API, but the Twitter API is very difficult to use. And in Python, we have two packets, okay? The one is called Tweepy, okay? Which is what we cover about here, okay? Tweepy. So it's a library wrapper of the Twitter API, okay? Another solution is actually bypassing Twitter, okay? So this is the Python wrapper of a Twitter API. Twitter API is just the request URL, right? So the how you set URL, okay? And there's old Tweet 3 or something, right? So there's another library. Yeah, this one. This is actually not using Twitter's API, right? It's like because the Twitter API does not allow you to collect old tweets for analytics, right? You want to get old tweets 1 year ago, but that API only provide you support for, if it's more than 1 week ago, you cannot get those tweets, okay? So that's why the older Tweet 3 actually bypass this. And so it's like a scroll in your browser, right? In your browser, you can visit them, right? This packet just like a scroll your browser to historical tweets and then wrap it into a library and send it back to you, okay? So these are the common libraries, okay? If you want historical tweets to do some analysis, then use older Tweet 3. If you want the most up to date, the current tweets, like live streams, then you can use Tweepy, okay? So yeah, we'll look at this code shortly. Okay, let's take first look. So to crawl tweets, you first need a developer account. This is not if you have a Twitter account, you can use it. Okay, you need to open your developer account. Basically, it's the same account, but you need to say, I want to enable my developer account, right? So that you can use the APIs. So here's a mini project about like you put some keywords, right? So for example, here we are saying the opioid crisis, right? We are interested in like opioid, right? So morphine, those kind of words, and people discussing this and see analyze like things right there, okay? And we put these two keywords to track, and this filter will run forever, right? So you need to cut it, okay? Otherwise it will run forever. And basically we have a, let me see. I have a folder here. You can see we already covered, this is a real word, not many people are discussing it. If you use some popular words, it will increase really fast, okay? Because it's capturing the live tweets, new tweets, and then capture it if it has a keyword here, okay? So you can see right now at 250. After we discussing the slide, it will go larger than 250 KB. Okay, we will see that later. Basically, it's a file where each line is a tweet, okay? But in the JSON format, though, okay? Let me, right, so each line, you have a timestamp and what's the content, etc. Okay? And whenever new tweets comes, it will append to the next line, okay? It's a real word, so it's maybe many seconds that one tweet capture, okay? And so, yeah, so yeah, let's go back to the slide, right? So in the project, we ask you for running for 1 day, right? So then you analyze those tweets, okay? And then you can also get the tweets because maybe you zoom into that user. Hey, that user is interesting. I want to look at what its friends are talking about, who is following that user, okay? Right, and so you can do some analysis over the crowd data set, right? So this was the previous project that we can scale, okay? So this is a Tweepy API, right? So, and it's a written in JSON format. JSON is originally, JavaScript, right? Object, okay? A JavaScript way of organizing objects into strings. Right now, Python is strictly using JSON, okay? But JSON and Python are very similar, except that JSON thinks that everything is a dictionary, right? So object itself is a dictionary. Right? Python is internally a dictionary, but it still have the OOP component exposed, like in C++, right? And frankly speaking, internally, Python object is a dictionary, okay? But in JSON, when you have an object, it's written in a way that it's like in Python's dictionary. Okay, that's quite interesting. And the benefit of those is that for each object, you can add another field with a particular name on demand, right? In like C or Java, you need to define the struct or the class first. Okay, you cannot change the object with new fields. Okay, in Python, it's just a new key value pair into that object. Okay, it's a dictionary. Okay, there's some URL documentation. I will share all these things online. Then later you can download if you have interest. Later you have bandwidth, like the summer, or you want to look into those things, you can check those slides. Okay. So here, how to make it work, right? So you need 4 keys here. Okay, right. So you need to request this. Okay, so this is using the called the OAuth model, right? So authentication model. Okay, so we have a demo, right? So you need to create an account. Right here, we are asking you to create new accounts, right? So then when you send us a Jupyter Notebook file, those accounts are not your account, right? So right, so we want to double check in case. Okay, so let me see. So this is justify why we have this. So these are irrelevant now. Okay, let me see. So Twitter developer accounts originally just push a button, you are able to use it. Okay, now you need to several rounds of emails. Say why I need this account, what I'm collecting. I'm not doing something sensitive or damaging to the society or something, right? So it's a very useful stuff, right? It's very, I'm doing something like meaningful, right, and helpful to the society or something, right? So I think they add some scrutinization to this to allow you. Okay, so this is Gmail is important. Right. So here's a Twitter API. Okay, so once you go to the apps or twitter.com, right? So you will go to page where you can open your developer account. Okay, again, it's your same Twitter account. You can open the developer account, and then you need to submit your application, right? So here, because previously we let students apply and we have 100 students, right? Everyone is saying, I want a Twitter account, right? So then I think Twitter get crazy. So we are saying, hey, how you write email correspondence to them, okay? Right, so here's an example, right? So then once you get approved, you will have this dashboard, and you can create an app where basically you can then you can start analyze tweet data. I think these are but this is getting approval. Okay, if you click the open, right? You create an app, create an open account. Okay, you will be required to fill in those information, right? Why you need the account, what you want to do, right? You are doing something not bad. Okay, because there's a privacy issue. Okay. Frankly speaking, I don't think there's any issue because Tweet's account, if you don't set privacy requirement, everyone can read it. It's just using computer to crawl. It's much faster. Okay, but again, they make it more rigid. So you need to describe why you need those things. Okay, so some text. Again, you can look at the slides later, and then they will tell a confirmation. Hey, your request for API is under review. Okay, and you check, and when it's approved, so they may have multiple rounds, right? So what's the intention, etc. Okay. And then you tell them, hey, what's the intention, and finally you will get approved. Okay, so it has been approved, and you can use a Twitter account. Okay, so the thing is that once approved, you will, so yeah, here's the process. Okay, create an app, go to apps or Twitter, create an app, describe why you need it. Okay, and then you will get those tokens. Okay, these tokens. And these tokens can then be used by your Python code with TweetPay, okay? And to cross it, right? Actually, TweetPay is just wrapping it into a crypto API URL with a key for authentication, okay? Right. So the first demo is how this process can be done. So I just run it already, okay? So you can install TweetPay. After installing, after authentication, after approved, you will have those keys and you put there and create some objects that allow you to crawl. Okay, and we are using the streaming API. Again, this code will be shared, so I will go really fast. Right, so you can look into the library, etc. yourself, and it will study. Okay, so here we are saying, hey, I want to open a file and append append lines. Okay, right. This file name is opioid.json, so that's why we have an opioid.json here. Okay, you see this increased a little bit, right? 342, previous to 250. Okay, or you keep it crawling. It will run forever. Okay, if you want to stop it, you have to stop it manually. Okay, for example, I stop it now. Okay, it will have error, but it's fine, right? So basically, we get some tweets. We get some tweets already. Okay, the JSON object. One thing that you might want to pay attention is because you interrupted the program manually. It might happen that it writes in the middle of this line and the ends. Okay, you want to check whether this line is complete. And if it's not complete, you delete it, the last line. Okay, let me see. 70. I'm not sure whether it's complete or not. I just play safe and yeah, let's look at this. 70. It seems that it's complete. Okay, right. But let's just play safe and delete it anyway. Okay, since the previous lines must be complete. Okay, let's save it. Now the rest of the code is showing what you collected. So you can load lines. Okay, and this is just this is just using JSON's packet. Okay, and you can see the content. Right, JSON is essentially a dictionary. Okay, additional embedded dictionary of lots of things. Right, and once you have those maybe 70 tweets loaded, you can get, hey, this key I'm interested in that. Right, so here we are interested in what's the Twitter ID and what's the text. Okay, and we iterate through that file and. Here are the content. Okay, so this is the Twitter account ID of that user. Right? So in the tweets ID, I think. Sorry, right? And this is the words. Okay, I think it's because our words are like opioid, right? So then I think opioid has become a problem here, right? Because we have some around the shop around the campus. Okay, so. Yeah, but so anyway, so it's like a drug, and there's some discussion, like spend a lot of time in hospital, but because opioid is another like a way of like painkiller, right? So so some are medical use, some are abuse. Okay, right? So you can take a look at what's there's a pressure and you want a relaxation, right? So something. Okay, so you can see something relevant to your keywords. Okay, mental health assistance, something like, right? So, yes, so then you can see whether something are legal use, some are illegal use, etc. Okay, right? So and some may be abused already in bad health condition, etc. Okay. All right, any question about this? If not, let's continue. Okay, so we have other demos, right? So, this is a demo we did already. Okay, crawl tweets from keywords, and crawl tweets from a user. Okay, so we have another demo. Let me see. Yeah, so this is so previously we used Tweepy, right? Demo that you can use keyword. You can also get friends. Okay, let me see. Let me get back to the previous place. Okay. Okay, let's run this again. So here, actually, you can use the ID, right? And using this URL, you can get those tweets what you want. Okay. So here, for example, I'm interested in this user, right? And the username. Okay. Then you can get this user and its information, how many people are following it, and how many friends it has. Okay. They can do a lot of things. So you can look at the Twitter API or the Tweepy API to see. Okay, these are the friends, right? And so there are two kinds of, right? One is called friends, where you are following other people, right? And one is followers, right? Maybe other people are interested in you and follow you, but you are not interested in them, right? So then they are not friends. Okay. And so these are the usernames, right? Twitter account names of those people, or screen names. Okay, and then you can get their information. Okay, so here is so this is if you get too frequent and there are a lot of friends, you are in trouble. It will say, hey, you send too many messages, it will fail. Okay, so we have some sleep. And here we can see that we use a cursor function, right? And get the pages of the followers. Okay, so here we are demoing two ways of using the API. One is directly do this for loop, but you can use the friends. Okay? Another, you can find the followers, right? And you can use the cursor function and the page by page. Okay? And here you are exhausting all the pages, right? Because the iterator, you go to the last page. Okay? Right? So you can see this guy is having super long followers. I think a tweet has a change of the ID length, right? So you will see some are old length, and they try to double the length in some way. Okay, so the tweet ID is becoming long, and these are the list. It's not done yet, right? So you have the dot. Okay, it's a very long list of followers. Okay, and then you can explore, right? So I'm interested in this user, right? And let me find this user, right? So then you can get this user. Okay. And then you can see who is this user, and you can get the other information about the user also, right? And you can continue from this user. Then you can go to that particular tweet, and you look at the tweets, and you are interested in these tweets. You can get this user ID, right, and the follower, and you can like screen name, and this thing can go back here, and you can repeat this process and explore the social communication network. Okay. Again, so. Yeah, so this file will be shared with you. If you have interest, you can take a look. It's just a demo. There's a lot of other things you can do, right? And yeah, this is a friend and follow. So I think this one should be crawl the tweets from a user. I think, let me use this. I think this is this one, right? So you can actually get the tweets of a particular user, right? So previously we are talking about who is following you or who you are following, right? So or a particular person following. But you can also look at what this person or the friend is posting, okay? Right. So let's go back to the same user, and we say, hey, we want to just 3, because for the purpose of demo, right? You can go to 200, I remember, maybe, okay? Then you get, hey, we really get 3, okay? Sometimes if you request too many, they will only return you some, right? So for example, I think you can request to 1,000, because it's a network communication, it will take some, but it only return you 200. So the upper bound is 200, basically, okay? Let's go back to 3. We don't need so many. Okay. So they don't return you more than the latest 200 tweets in time. Okay. But you can use the older tweets, right? The older tweet 3 library. Okay. That will get you all the historical tweets for that user, all the way down to the very early stage. And so then you will get a so-called this is parsing the object, right? And then you can get the text, right? So for example, this is the one tweet ID, this is the tweet information, okay? Just tweeting. And you can also, so let me see, what is this? Explore API user timeline JSON string, okay? For user timeline, okay? This is a time travel, right? So you can travel by time, okay? So for example, if we require 200, okay? And then we get the data list. Then you see, so here we are just look at a particular field, right? When it's created and what's the text of this tweet, and you will get a lot of these. Okay, you will get 200 because we can only get 200. You get more than 200, it's not helpful. Okay, and then you can even you can even flip the page back. Like this is going backwards because tweetp is like the current time. Okay, you are historically going backwards in time. Okay. Right, you can say, I still want 200, but I want to start from some historical point, 10 pages earlier, right? So you can do that. But I think all the tweets is doing much better. You can get the timestamp. I want to, from this date to that date, all the tweets by this user, it can crawl for you, okay? And yeah, so these are basically the information, okay? I think maybe page 18 is the upper limit. It doesn't allow you to scroll back more than 18, okay? So there's some limit on there. But 17, you will still get some data. So this is what we want to show, okay? But if you go beyond the 17, there will be nothing, okay? So there's a limit to control, so you cannot go beyond that, okay? Any questions so far? If not, I think this demo is okay. We will share the relevant files and slides there, okay? And yeah, this basically finishes this description. Okay. Oh, I see a chat. So, oh, so there's a Okay, so there's a suggestion that we can walk through the final project, right? So in that case, I will stop describing other data sources, okay, and instead describe a little bit the final project as a GP notebook file for the final project. Okay, let me get it from somewhere. Yeah, is this everyone want to have a brief walkthrough of the final project? Okay, so I got some yes. Okay, so if that's the case, let's take attendance. Okay, and the quick attendance, and then we will go back to the final project. Okay, let me go to here. Okay, so we'll take a really quick attendance. Okay, so I think Kamal has already talked about so confirmed. So I will just take him. And we will sample some students randomly. Okay. Gayatri, we will sample 10.
I'm here, Professor.
Okay. Suanzhou Li, are you here?
I'm here.
Okay, thank you. Aditya, are you here?
Yes, sir, I'm here.
Okay. Piyush, are you here? Piyush?
Yes, Professor.
Okay. All right. Hamid, are you here? Hamid Wadud? No. Okay. Wood Glass?
I'm here.
Okay. Mahesh Bang? Mahesh, are you here? No? Oh, I already sampled. So Vasha, are you here? Vasha? No? Sravan, are you here?
Yes, Professor, I'm here.
Okay. So just to be fair, we will sample the last student, okay? Because otherwise we will not sample to the boundary, okay? Abhishek, are you here?
Yes, sir, I'm here.
Okay, so that's all. Okay, we sampled 10 students. All right, so let me go to the final project. So let me see. Assignments, final project. So this is the file that you can download from Box, okay? And I think you can just download this. Okay. And then you will, let me put this here. Do we have another screen? Yeah. Let me put this to desktop. Okay. Now this is our previous tweet demo. I cleared it. Okay, so and you basically I create this Twitter, this and this folder tweet demo here. Okay. And let me see. So it's still downloading. Let's download this file first. Okay. Okay. Yeah, this is done. Okay. So let me get the file here. So what you can do is you can, after download, you put them here, right? So let's get the project file down here. Okay. And here you can take a look at these two files. Okay, right. So, so by the way, there's one requirement. Okay, the requirement is that you need to, I think you need to do data augmentation, right? So we have a requirement in the slides. Okay. Let me search for it. We wanted to do some data augmentation. So basically, this image, we don't have too many samples, right? So what you can do is you can flip, right? So left to right, or up to down, it's the same shape, right? If you move around, it's different scenario. But if you flip, you rotate it, to the computer, it's a different pixel setting, but to you, this is semantically the same, right? So you still want to do the same task. Okay, this will increase our sample size. Okay, you flip like left, right, upside down. Okay, you can also rotate actually. Right? So rotate, then it's a little bit complicated. If you don't want to rotate, you don't have to do that. Okay, because if you rotate, it will become some shape like this. And then you need to do some cutting, etc. Okay, but because it's a circular one, right? So if you rotate, it will always be meaningful, right? So actually, I think rotating need more work. You need to detect the boundary and erase the other things, right? And you rotate only the internal part, right? So this is super complicated in coding. Maybe you don't want to do that. But for the other data augmentation, you can actually go to my website. And if you go to, there's a, let me see. There's a deep learning one. Where is it? I think there's a video. Let me see. Maybe I didn't put it there. Let me find it and put it in the chat. Okay. Or maybe here we have TensorFlow. Let me see. TensorFlow. Yeah. So this is a comprehensive this entry. Okay. So if you go to this entry. So there's a tutorial. Okay, so this is a series of tutorials. Okay, I'm not sure whether you will have time to get everything, but you can find the useful things you want, right? So for example, for the data set, in our code, we have the TensorFlow data set loading, right? But we've done this for you. Okay, you just continue with the data set, right? So the loading part is done for you. And you can do data augmentation. You watch this video, how to flip left, right, up, top, down. Okay, you can do some, as long as you do some data augmentation, that's fine, okay? Right, because this will increase our data size, right? If you do 2 flips, this will, like, each flip will double our data size. Each time you will, like, it will make our data 3 times larger, basically. Okay, you can train more stuff. Okay, so for example, you can watch how the data set is object in TensorFlow, and how these. Okay, these are very good tutorials, basically. Okay, you can follow that, and each is like 15 minutes, etc. Okay. Yeah, so there are some useful stuff, link I put on my website. Okay. All right, so what you need to do is when you flip, you also need to flip the mask, okay, keep in mind. For example, here originally, let's say this is a 1, 1, okay? And this is, let's say this is 10, right? Okay. After flip, you need to adjust this to be, this is still 1, but this will become 9, okay? Right, so you need to change the mask pixel positions also. Just a simple calculation. Right? So all the coordinates is the largest value, right? The width minus the previous coordinate. Okay. Any questions? If not, let's look at what we provided for you and what you will be doing. Okay. So in this folder, you can see that we provided you lots of things. Okay. Here, firstly, we have the data. So the data are all what you provided, right? If you remember, you upload the CSV file, and we just put it and as a. Let me see. I need to get the. I think I need to get to the GBit notebook. Okay. localhost. Yeah. So if we go to this folder, we just download it. This is a Jupyter file. Okay. So here we already did all these for you. This saves you already a lot of time, right? So these are the annotation file, okay, and these are the images, right? And these are all contributed by the students. We select good ones, by the way. Okay, we only select good ones to avoid training. Have bad samples. Will if you remember, we have the mask, right, which we want, and this is the input image, right? Student has the annotations. These are the Y, annotation is Y, image is X, okay? If the Y is not good, then if theta X, right? So this supervision of the Y is wrong, then your prediction will also be bad. That's why we only select good ones. Oh, Vasha, right? So Vasha, okay, so let me see. Oh, attendance. So let's fix that later. Okay, so at the end of the lecture, okay, when the lecture ends, just remind me again, okay? I will fix that in one batch if you have attendance issue. Let me see, I think I am using the wrong. Okay. All right, so these are the images and associated CSVs we already collected for you. And this dataset folder. If you just put it here and run this Jupyter notebook, we will load these things for you. And there's some utility for visualization and these libraries already encoded for you, right? So you imported those libraries, utility, right? Also visualization package. So that saves a lot of the coding. Okay. So what we do is, hey, now in the current folder, and there's a data folder, right? We have a CSV for annotations and this for images. And we define, so these things are what you need to pay attention, okay? Each annotation object have label, X coordinates, and Y coordinates, right? So these are the polygons, right? So, yeah, again, so Vasha, can you remind me at the end of the class, right? If you left before then, I will not do that. Okay, so, and there may be other students. I will do that in batch. Okay, after the class, I will say any questions, and then you can let me know either by chat or not now. Okay, thank you. Right, so here you can see, you think about it, we have an image, right? Each image will have an image name, right? So a particular image with a lot annotations, right? And it has a list of annotation because you will have multiple cells annotated. It's okay? Right. And so here we have an object called image matter, okay? So which loads, and this image, each image will have a file, okay? With a file name, okay? And it's also associated with a list, right? Annotation list. Each element in the list is of this object, okay? Where you will have the class label, which we really not care about because we'll do segmentation. Right? Each pixel either foreground or background, boundary classification on the pixel one, okay? And 1 means it's a cell pixel, 0 means it's background pixel, okay? And then it has a polygon coordinates, right? So these are the X coordinates, these are Y coordinates, okay? Because this is X1, Y1, X2, Y2, X3, Y3, X4, Y4, right? So these are recorded by, but this is just one annotation, okay? We have a list of annotations, each is of this type. Is it okay? This is just the Python OOP, right? So class, define some class, and then we actually finish the code of loading from those files, all the training data and the test data for you, okay? So these are the loading, you see the file reading. If you have interest, you can read it, but ultimately, just know that we have those. So each image is now an image matter object, and it has a field which is the annotations, right? Which each annotation has a polygon coordinates, okay? And in the meanwhile, we also have the image file name. The reason we need this is that you can load it, right? So because images are much larger, we only want to load it when we actually need it, okay? If we don't need it, we don't load it, right? But you have the name, you know where to load it because you know the folder, you know the name, right? So it's just called the load image function. It will return the image, right? And then you can pass. So these code are already written for you, okay? Then you can. So here this is the test, right? So for example, after, let me see how to see this. So you can create an image object, right? And then you pass the file, okay? Pass the annotation file, okay? And so this is one annotation file, and and the annotation file. So this is still the testing, okay, to make sure things are working properly. And then we print what is in the object. So you can see we have the image file name, okay, and a list of annotations. This one polygon, another polygon, they are all like classes like this, okay? So we can show that we are successfully loading, okay? So in this project, you really don't care about how to read the file, etc. You just know that these things have been loaded in memory as image matter objects, okay? Right, so this is what you need to know, right? And you can load it to get the image, right? And this is, then you can also call the object load image function we showed earlier. You can print it, right, okay? And you know its shape, what's the shape, because you have the pixel tensor, okay? And then you can, so now this is debugged to be correct, right? So, because this is prepared by Sami, one of my PhD students. Okay, then we can pass all the annotation files, right, one by one. You list all the annotation paths, and because the annotation test says which data file is, right? So we can use the annotation file to set back to the data file, okay, right? And then you can load everything here, okay? And then you get a list of image matters, okay? So this is the original image. So right now, by this step, you don't need to change anything, okay? Right, this is done for you. We have this folder, okay? We collect from students and the claims and make sure they are high quality. And then we write the loading part for you. Now you assume that by this point, you already have the list of images. Each image has its annotation as another list, okay? And we have 83 samples, right? If you do the flip, it will be 166, right? One flip. If you flip again, at another 83, right? Vertical, horizontal, okay? Again, rotation, we don't require to do rotation, but you need to show that you do some segmentation, you do some augmentation, right? This will help. For example, you can flip this, right? And that's because we explicitly require this, okay? You can flip left, right, and top, bottom, and triple this size, okay? Right now, we're not doing this. Any questions?
Yeah, quick question. So when we're doing augmentation by flipping, do we have to change the annotations as well, or the?
Yeah, exactly. You need to change the annotation for sure. So, so basically you have these coordinates, right? You have these coordinates. If you are doing, let's say vertical flipping, right? So you let's say the width is W, okay? You need to horizontal flipping, right? Your X should be W minus 72 instead, right? So you need to, you have X, Y coordinates, okay? You can do this kind of change yourself, right? Just write a for loop and change all those X, Y coordinates. It's okay? Yeah, but you need to test it, right? So we have the visualization package. You need to double check whether it's working, right? So maybe X, Y, and Y, X, it's different, right? So maybe you think it's X, it's a height, and actually it's a lot of width. Right? So you need to have to flip just to make sure you visualize your change the annotation and the flipped image, right? And see whether they align, okay? Still correct align. Is okay?
Yeah, thank you.
You're welcome. And you can directly flip this object. Okay, if you like Sami, he actually wraps this into, TensorFlow's dataset object. You can see, right? So we have a TensorFlow dataset later loader, right? So basically we use this list we already got and pass it into the TensorFlow's data object. Okay, if we are doing this, then you can use TensorFlow's data augmentation functionality. And for that, you can watch that video that I shared. Okay, I didn't share, right? So you can go to my website and take the second entry of the blog and find that video for data augmentation, because it's assuming you already have the TensorFlow's data set object. Okay, and so one requirement is you need to flip maybe for vertically and horizontally. Okay, and here we are visualizing. Okay, you use this visualizing package that we provided and called the display masked instance, where you put the image file that you loaded, right? And you put the annotations, okay? And you put the masks that you provided, right? So this load mask is because we wrap it into the dataset object. Dataset object defines the load mask, okay? So we have the load mask, okay? And then you can throw to this visualization function. Again, you don't need to care about the details of visualization function, you know that if you provide the image file, you have the annotations and you have the mask, right? And then you can show it correctly. Okay. So here's an annotation, right? This is still polygon by the students. You can see this is of super high quality. I think the student did a very good job. Okay. And again, we just choose the high quality ones here. Okay. And if you want, you actually in the data loading part, you can kick out some of them. Like this is not so colony-like, right? It's a multi-colony. Okay, so if you want, you can kick out some of them. Okay, and it depends on the label, class label. Okay, but anyway, so this is visualization, right? So and this part you don't need to change, but you need to know how to use it. Right after augmentation, you check whether the augmentation is done correctly. Okay. After that, this is what you need to do. Okay, if you remember, we have a requirement here, right? So let me see. Right. So image loading is already done, as we said. Okay. Data augmentation is what you should do first. After that, so this is what you need to do. We do the segmentation training. Okay. So we already demo how you can train a model and make it function, right? For you already. Okay. Using UNet. Okay. But we have a list of other models that we want you to try out, right? So so you can select any other models except for UNet. Okay, so let me see. So like these models, and we actually provide the GitHub link. As long as you know how to use a model, walk through their examples. Right? We know that you may not be familiar with deep learning internals, right? But if people code the model, you understand how to use it, you should be able to use it, right? So you can select a few models, right? This may be DCN, this is FCN for the convolution net and the dense net, right? And dilated convolution and deep lab, etc. You can choose some, right? If you have interest, you are doing a group project, you want to do an awesome job, you can try to compare what deep lab v2, deep lab v3 plus. What's the difference? That will be a very meaningful project for group project. Right? If you are doing it alone, you just pick one particular model, like FCN, how it works, right? And you can compare with the already provided, unit. Okay. Right. So if you are doing it individually, you need at least one model, right? If you do group project, we require at least 2 models, okay, more than one model. Okay. Otherwise, it's unfair to the students doing this individually. Okay. And again, we have you can see there's the libraries, and they tell you how to use it for sure in those libraries. Okay. You just now your input is already here, right? So input is input it either if you don't want to use TensorFlow's dataset object, maybe they don't use a TensorFlow data object in their model, right? They have some other object type, right? You can convert this like adapter into their object, like this field go to there, etc. Okay, so this is one way. Another way is if they, a student asks for bonus points. Of course, we will consider that. But you need to have a report finally and explain what's the additional stuff you do. Okay, if you just accomplish all these things, then we will give you a very good mark. If you do additional, we can consider bonus. Okay, maybe go beyond 100 to almost maybe 110, etc. Okay, that's also possible. But you need to explicitly mention that in the report. Otherwise, we will just mark based on the criteria, augmentation and model comparison. Okay. And here, this is a example prepared by Sami, okay, my student Sami. So what it does is, it converts the image matter objects into a, this is a data loader called by this function is a function to this dataset object, right? Then you will create from our list of images in memory, image objects in memory into the dataset. Then you can use TensorFlow 2.0's way of doing that, right? If that particular model is using this dataset object, then you can directly use it, okay, right? Otherwise, you need to go back to the image matters, right? And then convert to their input format, okay? In this particular case, Sami is hard coding this model, okay, right? And if you have interest, you can also hard code it, right? So basically, Sami say, hey, which layers we want to do, come to the encoder, decoder, right? So those libraries may already code this, right? You don't have to code this yourself. You can use the GitHub Okay, basically they are doing this for you. Okay, and then you can train. Okay, so in our case, so the training is super time consuming. Okay, make sure you use Google Colab or a GPU machine like Chiha, our Chiha cluster. Okay, like somebody train UNet, I think it takes 10 minutes on a GPU machine, but if you train using a standalone machine, it will take hours. Okay, it will be slow, and if you have some bugs, then you need to fix, right? And the tune parameter, it will take even longer. Okay, and here you can see that you can let me see. Kernel, change kernel. This is Python 3, right? So I think you can enable GPU. I'm sure Google Colab provides you GPU for certain maybe 24 hours. Before that, after that, it will not allow you to use. Okay, I think there's let me see. Environment tab. I don't remember right now, but there's some tab you can say you want to use the GPU. If by default it's not using GPU, but I think by default you are equipped with the GPU. Okay. What did I do? Sorry. Where's the GPU number file again? Oh, I deleted it maybe. Right. So let me see whether I can. Yeah. Let me see. Oh, it's here. Sorry, I closed it. Mistaken. And it's because this file is again a content, right? It's a browser to interpret. It's just a website. So if you have a lot of content, it will take some time to load. Okay. So here you can see that we actually this is a typical way of using dataset object in TensorFlow 2. Okay. And we have a video, right? So for augmentation, before that, it's a dataset. You can watch these two videos, then you will know everything. Okay. And then you can display the samples, right? So here we are plot, right? So this is input image. This is the ground truth mask. Okay, we are just plotting in another way. Right? Previously we used a visualization, so you can see differences in different color. Okay, and now we are plotting only the mask. Okay, and in particular, you can see this aligns well, right? So these are the highlighted ones. Okay, and then we get the model architecture. In general, if you want to. You don't want to code yourself, you can just use the GitHub model, download it, and study how to use input output. Any model, basically you have the input, right? You need to prepare the input, okay? But we already have those image matters list for you. You just convert into their required format. And the output is, the prediction, right? So that's also our input, right? The output is this segmentation, input is this image, basically, okay? Right. And then you have a new sample, then you can direct the segmentation, and you don't have to let human labels them, right? So that's much nicer, okay? And this can be post-processed later. Okay. And so here we are saving the model, right? These are all TensorFlow, okay? These are all TensorFlow, and we are saving the model every few epochs, right? Every 5 epochs we'll save a model, okay? And finally you can load it and this is a compile, okay? And then train, okay? After training, this is a compile and you have a saver, okay? The model will be saved to disk. So to make sure you save the model, okay? Because training is time consuming, okay? Let's just think if you train for 1 hour and you forget to save it, right? And then you finish this file and you find, hey, I forget to do data augmentation. You come back and do it again, but you need to retrain the model, right? So of course, if you forget augmentation to retrain, but if it's for some other issues, then you need to retrain the model for hours again, okay? So make sure you save the current model you have. You can continue to train the parameters, tune the parameters, continue gradient descent from where you left over, right? You can load as a checkpoint, okay? And here we train for 25 epochs, right? If you just train 3 epochs, it will not be so effective, okay? 25 epochs, and then all these this model is basically TensorFlows, okay, Keras model, okay, and then train, and you will show, hey, this improves 44, 46, and then 55, right? So the performance improving, okay. If you see something wrong, then you need to adjust the optimizer and like so you can Google a little bit how to like learning rate, right? So you can adjust the learning rate. Right now we use 10 to the power -4, and usually you start from 10 to the power -3 and 2. And depending on whether it's improving or not, you can adjust the learning rate. Okay. And after that, you will save this model. This is very important. Okay, you want to save the weights. The weights are the theta, right? So you know. So machine learning basically gradient descent, right? So you go gradient descent here. This is the current theta. Okay, you need to save it. Okay, and the next time you can load it back. Okay, and then you continue gradient descent, right? So make sure you save your model, even if you are not at the best spot, right? You don't need to go to the continue train. You can just load and predict. Maybe it's already very good, right? And again, this thing is time consuming because you know, right? So you need to study a lot of things in this file. Okay, so after walking through this, I think you should begin as soon as possible. Now it's Tuesday. Till next Wednesday, you still have 8 days, right? So I would recommend you to start working on this as soon as possible. Okay, a lot of things you can just reuse, but for those other models, maybe you need to study a little bit. It will take some time. Okay. So here, this is just to show everything, right? So you don't want to see dot when you print a list or something, okay? And then we will show everything, okay? So here is an example, right? So this is a TensorFlow's model, okay? Once you train, then you can predict and you give a better image. Make sure the image is not in the training set, okay? For machine learning, you want to train with a portion of data and then test with another portion of data. Otherwise, it's cheating, right? Okay, so here you can see we have a training data set. We also have the validation data set. Okay, it's clearly split. Okay, let me see where the splitting. This is split. Yeah, here is what we are doing. Okay, so we have the data set, right? So and we have the training, we have the validation. Okay, and they are cut into like the first 90% are used for training. Okay. The last 10% is used for validation. And then we take it means, you know, skip the first 90% and take the rest, okay, 10%. It's okay? Actually, we don't need valid size, right, because it's only transit. But all these are data set functions of the TensorFlow data set object. Okay. Let me see. Yeah, I hear someone's talking, so let me, if you have any questions, feel free to ask. Okay. All right, so now after that, you need to visualize. We are using the same visualization function, okay, right? But we specify the color. Basically, we only want one color, okay? So here's the summit model training, right? So if you get the prediction, okay, the prediction, this is the mask, okay? And you put mask, predict mask here, and you do the visualization, okay? And of course, you need to do some type conversion. You can take a look at what's happening. Here we are just taking the first batch. Okay, so first we have a batch size of 5. If you look up there's a batch size. Okay, and we get the first batch, and we get a batch of 5, and then we get some image from there. Okay, so we have third image in the first batch. The first batch has 5 images. Okay, and then we show some information there. Okay, and then we visualize the prediction. Right, and you can see the mask, visualize the mask here. This is a predict mask. This is the image, right? This is the original image. This is the predict mask, okay? This color. So this is our prediction. If you give the image, the model will give those masks. It works okay. It misses a lot of things, but it looks okay, right? I think you can try different models and see what it improves. Here's the ground truth, okay? This is a ground truth where you visualize a sample mask, which is the mask you obtain, okay? And this is the predict mask, which is from the model, okay, from the predict mask. Okay. So because you need to show whether this performs well, right? You compare this with this. Right? It's okay, not perfect, right? But a lot of them are detected at least. Okay, so reasonably well. Right. And you wanna replace this part. You want to do a data augmentation and replace UNet with other models, okay? You don't have to replace, you can continue this file and starting from there, right? And then you can compare, for the same image, you compare how the prediction looks like and do some analysis, okay? And I think there are details in the paper, that, in the slide. We'll request you to do this kind of prediction, ground truth comparison in the validation of the test data set for maybe, again, this is validation set. You need to hold out some for test data set. Okay, so for maybe 10 of them, I remember maybe. Okay, you sample 10 of them and show the result. Okay. Yeah, so that's pretty much what the project is about. Any questions? For the question regarding the project length, report length, so I think the report should be like what model you selected, right? So your experience that you are working on the project, right? And then the sample images you can attach to the report, okay? And so also like you did what you did, like a vertical, horizontal flip, right? And what models you tried. And finally, you can get some analysis. You show, hey, this model is better than that, right? You're not maybe not performing well enough, right? Other model performs well. And you can also use the metrics we mentioned in the slide, okay? If you remember, we have the mean IOU, right? And these kind of metrics, okay? At least you have the accuracy, right? So for example, this is a 1-0 mask, right? This is also a 1-0 mask. And you can see whether what's the accuracy of that, okay? Whether here this is 1, this is 0, then it's fake, it's wrong, okay? If this is 1, this is also 1, then it's right. You see the percentage of correctness, correct predicted pixels. Okay. So basically 3 parts, right? So the first part is what model you choose. The second part is how you did this. The final part is some result evaluation, right? And I think it will take at least the 2 pages, right? Potentially some people can go all the way to 10 pages, okay? Right? Because if you show all these images, etc., right? But as long as it's clear, that should be good, okay? Yeah, so that's pretty much the project. Any questions? Oh, one thing is Kamal. Are you here, Kamal?
Professor?
Yeah, so as a PhD student, you need to do a presentation, okay?
Okay.
Yeah, of the project. And we can take a particular time that, and then you can do the presentation, and then we can share the video with all the students. It's okay?
Okay.
Yeah, in the past, we have a presentation by students. Let me see. Let me go to my channel. Let me see. Playlist. Right? So in the past, for example, in our machine learning course, we have students presenting those stuff. Okay. Let me go to here. Right, because we have many PhD students by that time, student will be presenting this. Okay. They will go through their reports and what they have and how they do these things. Right? And they can also present some code and what they did. Okay. And they do slides, etc. So you can take a look at the machine learning presentation last time and do something similar. Or if you don't feel necessary, you can do it directly. It's okay? Right, so yeah. So because this time there's only one PhD student, we don't need to have an entire class for that, okay? And so, yeah, so that's pretty much the project. Any other questions? Yeah, if you don't have any questions, I would recommend you to start working on this as soon as possible, right? So it has been released for 1 week already, right? So if you haven't begun, it will take time. Okay, I can tell you, it will take time. But I think the machine learning final project last time, I think the students also did a very good job. So this one is actually much simpler. Okay, yes. You just study some model and understand how to use the library, and we've done a lot for you guys. Okay, and just do some simple coding to make other models also working like you now. Right. Okay, so we still have some time, right? So let me see. We still have 6 minutes. I don't think we can go through a lot of things. We can. Let me see what I can do. Okay. Okay, let me briefly go through some other open data repositories. Okay. So for example, a lot of the time we are working with geospatial data, right? So, so this is relevant. Okay, so a lot of the time you want to do transportation or other related stuff or visualization, right? You need to get the road map, okay, road network. Okay, we can use OpenStreetMap for the purpose. Right? So basically, I'm not sure whether you've heard of this, but people will do the manual annotation of the road, etc., looking at the map, okay? And look at a satellite image, and they will share. And then people will plot, oh, this is a major road, that is another road. And then people will upload them. And then the OpenStreetMap will aggregate them into a roadmap, okay? And here, for example, we can go to the OpenStreetMap website. We can have a bounding box. Then we can download export all the data there. Okay. Again, we don't have too much time. I can share this file with you guys on the dynamic syllabus later. Okay. And then we can download. And sometimes it will give you an error because, but again, this file is an XML file basically called a .osm or OpenStreetMap, but actually it's an XML file. Okay. It's just using the schema of the OpenStreetMap. And sometimes it will tell you that, or you can also manually get an area, okay, right? Or you take the whole screen. By default, this is a default window. Okay, if you want to make it a little larger, you can manually adjust the coordinates. Okay. And so sometimes it will say, hey, you give a too big area, right? So I don't allow you to download it directly. Okay. Then what you can do is you have some options. For example, you can use those APIs to do that, right? For the larger roadmaps. Okay. So there's an overpass API that you can use. For example, it will take a while. Okay. And there's a Planet API, and there's also this dumps, right? So they directly dump the data as a zip file. Then you can directly download the data. Then you don't have to send a query to the server once you're online. Okay, they dump all the entire continental data for you, right? So basically, you can get the entire road network of maybe Asia or maybe USA, right? So so this, as long as it's shown there, right? You can get the whole roadmap of Europe as a dump. And if you look at the data format, right, so it's a relay node, right, road intersections, right, and where the GPS coordinate, okay, and then the edges, right. These are what are the nodes, and these nodes connect to a way, so we have the way. These are roads, okay. And again, there's some other metadata, whether it's a highway or what's the name of the road, etc. Okay, like this is in Chinese, right? So this is the Dagu North Road. Okay, so you will get a lot of information there, and the schema is in OpenStreetMap. Okay, and so you can also get some shape. This is for some district, right? It's surrounded by different roads. Okay, what's the district of it? Okay, and you can also see different kind of buildings. It has a lot of things there. Okay, you can see Costco even there. And this data will be super useful. You can parse the XML, right? And then you can, I think OpenStreetMap potentially itself has some API, and then you can do some analysis using that. Right? And the rest, I think, is relevant to the data chronicle. Okay. And another important data source is like a US Census Bureau. You can get, let me see. For example, one example is a Tiger Web. Okay, you can, let me see whether we can. So this is the US Census Bureau. They actually share a lot of data with people, okay? And they also have the API. For example, Tiger Web is focusing on the map services. You also have some demographic features, okay? And there are some API for you to crawl data. And again, you can do things like this, right? And you can choose some, here you can get all the school districts and a lot of data here, right? So, and what's a road, if you want to transportation road, and you want to zip code areas, right? So you can do a lot of things. But again, it was a boundary of zip code area, but because we don't have the time, so yeah, so I will upload those slides to Canvas, and if you have interest, you can take a look at it later. Okay, so that's the end of this lecture. Any other questions? Because I don't want to go over the time. Okay, so these are the API used in the latest slide. Okay, how to formulate the query, and choose a particular server. Right? Yeah, and Okay, so that's all for today. And I know this is the final class week, and then we have the final exam week, right? So 2 weeks to go, so quite busy, right? I hope you will survive it and get a good grade. Okay, thank you. And any questions? Otherwise, that's the end of the class. Feel free to leave. Okay. You're welcome.
Do you know what day the final is off the top of your head?
Yes, sir.
Oh, by the way, for this course, we don't have final. Okay, we have final
Okay.
project. We don't have the final exam. Okay.
Gotcha. Final project. Gotcha.
Final
Gotcha.
project is equivalent to final exam. In
Got you. Got you. My bad.
Yeah, you're welcome. Data science is really hands-on stuff. If you do a lot of theory, it's not that helpful. Okay, even though we have two homework, right? These are very important concepts, but I think there are also libraries you can call. Understanding a little bit of the SVD and the streaming algorithm is good, right? Most of the time, it's like studying how know the library and call the library and apply them to your project. Okay. Okay.
When do you think you'll have this video up? Maybe tonight, maybe tomorrow?
Can you repeat the question?
I said, when do you think you will upload this video, this lecture video?
Tonight. I will.
Tonight.
Yeah, slides and video by tonight. Okay. Tomorrow you surely will see it. You're welcome.
All right, I'm running away. Have a good day.
You too. Yeah, because this is last class. If you have a question, last chance. Okay.
Professor, when will we get the grades for the homework assignment and the image annotation for the second submission?
Image segmentation is already there, right? So in the folder, right? So
we got a second chance to upload this image segmentation.
I think it's already done, right? So you need to communicate with the TA. Okay, I think the TA already, because after the second batch, we actually cleanse the data, and it's already in this folder. Let me see. It's already in that folder. I think the Jupyter notebook, we have the folder of data and annotation. It's already there. If you want a second chance, you need to. It's already too late, but we will see. We will have some late penalty. If you still want to do that, we can discuss. Okay?
No, I did. I submitted it the second time before the deadline. I just haven't gotten the grade yet.
You still haven't got the grade? No. Just send the TA email, copy me, okay? So I can follow it up. It's okay?
Okay.
Yeah, because usually the TA is following this, right? So just let me CC me, okay? I will follow up and make sure it's graded. Okay.
Thank you.
You're welcome. All right, any other questions? Again, this is the last chance. If you have ungraded assignments or all those things, just let me know. Okay. So the second assignment, will, I think the last week we'll grade and post the solution and the grades. Okay. Okay, I don't see any other questions. And then have a good evening. And good luck with the final exams.